Hello everyone, welcome to this session. We are going to talk about the mass balance and the law of mass conservation. Surely you have heard about the conservation of mass law, but how do you apply it to a real life scenarios? Well, for example, what do the growth of a plant and the rusting of a truck have in common? Well, the mass transfer. These two processes involve mass transfer. So the objective of this session is to study the conservation of mass law. This law describes the fact that the total mass and energy in a system remain closed. We have in here the example of three systems, an isolated, closed and open system. And we describe in here the exchange of energy and the exchange of matter, which is only free in an open system, as you can see. So that statement of the conservation of mass incorporates the fact that the mass and energy can be converted from one to another. The equilibrium in these systems can be used to track the contaminants from one place to another through chemical equations, and this helps us to identify constraints in the system. Derivatives and integrals can describe the fluid flow through equipments. These tools are broadly used in contaminants analysis in the environment. Well, this in the theory of systems can be very useful, but how do we apply these concepts to real scenarios? For example, the growth of a plant involves some mass transfer of the components for the plant is transforming to the plant good growth. So how do you apply this law to these scenarios? You can use this useful tool that is called control volume. That it's a boundary that we set up. It could be any shape or size, even the size of a plant growing, of a truck, and it can be also a mixing tank or a thermal power plant, and it helps us to understand the transmission of heat and mass. Let me go to the next slide. Then the first step to use this tool is to specify the control volume. So we have in here a control volume frontier that it has inputs and outputs and an accumulation rate and other reactions that can happen in here. Then the equation of the conservation of mass law can be described like rates. And the rate of accumulation is equal to the rate of mass entered minus the rate of mass exceeded plus the mass reacted. So using this equation, we can go back to the plant. Let's say that the plant accumulates 25 grams, and we have the simplified equation in here. Accumulation is equal to mass in minus mass out, so that there's some components entering into our system and some components exceeding our system. So the other we said that the other components are defined because the plant is searching its foods. Then it does through photosynthesis, that is in here, this equation. It's carbon dioxide plus water plus light energy yields glucose and oxygen. We are not using the light energy because we are only studying the mass in this process. So we have in here our system. A differential of mass is equal to 25 grams. Carbon dioxide and water are entered into our system, and we are obtaining oxygen. Then, using basic stoichiometry, we can determine the carbon dioxide mass. So we have the initial 25 grams of glucose, that is the accumulation in our system, and we can use the molecular weight, the inverse of molecular weight in here, also of glucose. We multiply by that, and we obtain the quantity of mole of glucose, and then we are using the molar ratio obtained from the equation. For every 6 mole of carbon dioxide, we obtain 1 mole of glucose. This molar relation, can be used in any way. We can use it like an inverse or like it directly, but in here we want to obtain the mole of carbon dioxide to multiply by the molecular weight of carbon dioxide, and then obtaining grams of carbon dioxide. For this case, 25 grams of accumulation in glucose, we need 37 grams of carbon dioxide. So for the other components, we also can use stoichiometry to calculate all mass balance. Also, with the initial 25 grams of glucose, again the molecular weight, and then here the number is the same than in carbon dioxide, but it's another relationship. This depends on the equation, the chemical equation we are using. In this case, it's the same number, but in other cases it might be different. So you have here grams of glucose, and then grams of glucose divided, mole divides mole, and mole of water divides mole of water, and you obtain grams of water. In this case are 15, and then we can also calculate the mass of oxygen. All these calculations you can see it in my YouTube channel, but it's the same procedure. So we have in here the molecular weight again. Another relationship, with this case is the same number, but it doesn't have to be true for any calculations. And in here we have 25 grams of oxygen for the process of a plant growing. So we put this on the accumulation equation, and we have the mass in, that is the mass of the carbon dioxide, plus the mass of water minus the mass out, and we have 25 grams. In this case, you can see that you obtain the mass of each component in the equation, the inputs, the outputs, and that's where we went when we are analyzing contaminants or other other components in the environment. So passing through the roasting track, we have in here a mass accumulation of 10 grams, but in this case, because it's a roasting process, the accumulation, it has to be negative, because the track is losing some parts. So the chemical equation in here would be the iron, which is the drug material. It is made by iron. We have in here the reaction, the oxidation, so it's iron oxide. Then our system and control volume is the roasting track. We have a mass in, a mass out. The accumulation is the mass in minus the mass out. In here it should be minus 10 grams. And then we also can do the oxygen and the oxide calculation. I don't know why it's not showing the oxygen, but the iron oxide, you can see it here, it is the same calculation. You have in here 10 grams of iron plus the inverse of molecular weight of iron, and then the molar ratio of the oxidation equation, and then the molecular weight of iron oxide, and then you have grams of iron oxide in here. So the next we have in here in the balance, the oxygen has 4.3 grams minus 14.3, and this is obviously 10. You can see here is very easy, but sometimes you have some contaminants that are not easy to see these relationships, and the conservation of mass law is very useful to track them in some path. And so for the final thoughts, the law of conservation of mass has served as a useful tool to learn more about the system, and control volume is a tool for solving problems in real world scenarios. So the conservation of mass law can be applied in any kind of scenario. Thank you. Bye.